It's great to be back here again. Always is. Bangalore being my second home. For that, I thank the organizers for making this possible every year. So today I'll be speaking about the network analysis of a protein family in continuation with several talks that I've been giving over the years. And this work is done in collaboration with my student, Pradeep Bhadola, who is now a lecturer in Institute of Fundamental Studies, Narswani University, Thailand. This is my group, bunch of kids trying to do this protein problem as well as the RNA problem, and some of them trying to do graphene as well as wild semimetals. So the plan for today is that I'll talk about proteins, give a little snapshot of it. As an introduction, you've heard about 3 or 4 talks in the previous day regarding proteins, so I'll go very fast here. And then I'll come to the system that I'll be talking about, the beta-lactamase family, talk about the system and the data, construct the correlation metrics, look at the networks with threshold, and then the properties, and conclude with conclusions. Okay, so in this slide, I'll just mention that proteins I will discuss as strings of repeating units of amino acids, which are 20 in number, and go ahead in the interest of time to the next slide, which is the system. And the protein that we'll be talking about is the beta-lactamase family, okay, which are proteins, enzymes, which are secreted by bacteria in response to antibiotics like penicillin. This is a penicillin, a molecule, and it's active, but the beta-lactamase protein deactivates the penicillin by hydrolyzing the bond here. So our aim is to find, to study the beta-lactamase protein so that we can find the positions of the amino acids which are important. Okay, so if we can remove the action, if we know the positions and then deactivate those positions or mutate it some way, we will control this process. Okay, and so the method that I'll be outlining is for in general for any proteins, or for that matter DNA, RNA. Okay, so we'll be trying to identify the important clusters and positions of this family of proteins. So we get the data from the protein data bank, which is this one, and it consists of 547 proteins in this class A over D beta lactamase. And there's a lot of noise there, which we can process and filter. And from the 547, we get a sequence of 559, which we then align in a multiple sequence alignment. This is the multiple sequence alignment in which the length here is 248 or so, okay, amino acids. And this is a string of amino acids, protein. And the number of sequence here is 559. Okay, so what we do is actually at each point of the amino acid, we put the property in, like for instance, the hydrophobicity property, and make a data matrix, okay, of size, length 248, and size here, number of strings 559, okay? And we do it for many properties, polarity, volume, etc. This is the heat map of this data matrix, okay? And the numbers have been scaled between 1 and -1, okay? So these are the properties, 8 properties, okay? So we have this data matrix. And from each of these data matrix, we can form the correlation matrix, which is the Pearson correlation matrix, and is defined as in this way. the usual Pearson correlation matrix. Okay? And these averages imply average over sequence. Okay, this is the distribution of the correlation matrix for these properties. Okay? Note that they are both positive and negative values. Okay? So now we'll be constructing the network. How do we construct a network? We take a property, and the graph is made up of the nodes, which are the positions in the multiple sequence alignment, which is 248 in number. So length is 248. Then the edges, E, are between the two nodes I and J. Okay? And if I is not equal to J, the correlation matrix, the Pearson correlation matrix between the I and J element, if it is greater than theta, theta being a threshold, okay, then we put it as equal to 1, or we put it equal to 0. So different thetas generate different networks. Okay, so each theta generates a network with the same set of nodes but different edges. And the connected components that we will find by changing the threshold will show the structural and functional properties of the protein. Higher threshold means that the links or the edges are highly connected between the positions. So this is a threshold 0.3, okay? And these are the different properties. And this is the network at threshold 0.3 for the different properties. Note that they are very highly connected. Okay? This is optical, this is hydrophobicity, polarizability, and so on. Only the non-zero degree or the non-zero link nodes are shown. The blue line, I mean the blue color, tells us the negative average value of the property, whereas the red line is the positive value. Okay? And you can see even here that the network shows you that the red connects with the red and the blue connects with the blue. Okay? And you'll see this at different thresholds, at the higher thresholds as well. The blue connecting with the blue, the red connecting with the red. And you can see that the network is clustered now, okay? And there is of course this one in which a blue and a red is together, and you see the clusters forming at the different thresholds. 4 minutes, okay. So this is at a higher threshold, okay, there are more clusters, okay, and this is at 8, okay, and this happens for all properties, okay, this small number of clusters. Okay. So now these positions are labeled, and all these positions are important, okay, and many of them are found in experiments. So what we've done here is take at a particular threshold, this is the hydrophobicity property, the property which likes water, the amino acid liking water, and we've reconstructed where those important positions are in the protein, okay, at the different thresholds. And this is some property, it's called the network density. And we've plotted the network density against the threshold here, the average degree against the threshold, the degree distribution for different thresholds, and compared it with the random network. The brown is the random network. And this is the average clustering coefficient. And yeah, with threshold. Okay, this is the position and this is the threshold, and the color is the is given here. Is the color code. I mean, the property is the color code. Okay. So, and this is the characteristic path length that was talked about, the shortest path between pair of nodes for all these properties and against threshold, average path length. Okay. And I conclude. Is that okay? Am I finished? No, good. Yay. Okay, so this is the conclusion. I won't go through it. The thing is that I'd like to mention that in the future we'd like to use machine and deep learning for the data analysis.